Hello students and friends. In this video we are going to see one analysis, that is a composition analysis of nanomaterials or thin films. This particular composition analysis is going to be done by X-ray photoelectron spectroscopy. So the name itself tells you that it is analysis of a energy matter interaction once again. And here the X-ray is going to be falling on the material and it is going to be interacting with the material. As a result of the X-ray matter interaction, the photoelectron is going to be come out of that material, right? So we are going to analyze the photoelectrons which is coming out of the material. And all of us know about this particular, X-ray photoelectron creation, right? So if the X-ray is falling on any, shell, the photoelectrons will be coming out of that, out of the shell, right? So the photoelectron will have a unique kinetic energy, and that kinetic energy can be converted into binding energy by means of this particular formula. So if you know the binding energy, that binding energy will be corresponds to a particular electron in a shell of a particular element. So if you know the binding energy, that binding energy being since the binding energy is unique for a particular materials, particular element, here if you know this particular binding energy, you can know about the element present in that material, right? So I'm not going to the theory. We are going to see how to do the analysis, right? So this is the data to which we are going to do the analysis. And here, so many data are available there in the sheets. You just see here, a survey data is there. And, there is something like called XPS survey scan. And here C1S scan is there. B2P scan is there. Then O1S scan. This particular O1S scan and 2VP scan and B2P scan and C1S scan. All these scans are core level, XPS scans. And here this particular one is XPS survey scan, right? So using this particular XPS survey scan, we are going to do a survey of elements which are there in the particular compound, right? So whatever the elements are there, whatever the number of elements are there in the material, we are going to do a survey, right? What are all the elements present in that particular material, like that, right? So for that, we are going to use this particular XPS survey scan. And here, from the XPS survey scan, we come to know that this particular compound is having vanadium and oxygen as a major content. So we are going to find out the ratio in between the vanadium and oxygen. That is, vanadium oxygen composition in a particular compound. And one more thing is that C1S scan, right? So this C1S scan will be there, inherently it will be there in all the material because carbon will be coming, carbon's XPS peak will be coming since most of our sample will have adventitious carbon in it, right? So from that particular carbon 1s peak will be automatically appearing in all the XPS scan, right? So if you want to avoid this particular carbon 1s scan, so you have to etch out the top few layers from your X-ray photoelectron spectroscopy measurement itself. During the measurement itself, you have to do that particular etch up, right? So if you are not doing that etching, so carbon 1s peak will be automatically coming. And one more thing is, based on this particular scans, analysis also like that, two things. One is XPS survey scan analysis. Another one is core level scan analysis itself, right? So in the survey scan, so here the data is there. The data is given as binding energy and its counts. So I'm going to copy this particular, binding energy and curve. And we have to, paste it in a separate sheet. And I'm going to simply plot it, right? So after plotting this, we have to find out the peak position of each and every peak, right? Fine position we have to find out. Most of the time nowadays, the XPS instrument itself gives you the chemical shift corrected data only. If it is not chemically shifted, we have to correct the data by using the carbon 1s peak, otherwise AU 4F peak, right? So here carbon 1s peak is given to you. All of us know that the carbon 1s peak's position is 284.6, right? So using this particular 284.6 peak position, we have to shift our XPS data. so that we can do that, chemical shift correction, right? So for example, here, this is the, your carbon oneness peak. To know the carbon oneness peak in the Excel, Microsoft Excel, you can directly place your cursor here and you will know the peak position. Since I'm not using Microsoft Excel, I am going to get the peak position from, QTI plot. And here in the QTI plot, I have the same, data plotted. So here, this is this is the peak height. So this might be the peak center, I hope. And this is 285.08, right? So 285.08, 280, 285.08. So that is the peak position what we got for our experimental data. But actual, carbon oneness peak position is 284.8, right? So we have to find out the difference in between them, and we have to add the difference to the data, right? Only to the x-axis we have to add the difference, right? So that is this minus this, right? So 0.28 binding energy, electron volt of binding energy should be added to the x-axis value, right? So for that, what we have to do is, so x-axis alone, I am going to copy it once again. So here I have copied. Now with this particular data, I am going to add, add panama. I think we have to minus it, because our data is 285.08 and the carbon oneness peak's original position is 284. So instead of 284, it is 285. So we have to minus this particular 0.28, right? So here I am applying a formula, that is column 1 minus, that is 0.28, like this, right? So now instead of 1350.08, now it is 1349.8. So I'm going to apply this particular formula for all, throughout the column. I'm going to apply this particular formula, right? Now I'm going to copy the intensity here, and now you have to, what is that? Plot these two columns, right? So insert, go to insert, chart, and simply XY scatter, finish it, right? Now this particular graph is, chemical shift corrected photoelectron spectroscopy graph, right? So here you can edit the, what is the scale or whatever you want, you can do it here, right? All of us know what to do with that scale and some, corrections and all, right? So here I have plotted my survey scan from 0 to 1000, right? So in between, I'm going to find out all the peaks. I'm going to list it. And for each and every peak, I am going to find out the attributed element, right? So for example, if you place my cursor here, that is 6 point, what here in the data will be visible here. That is 6.08. And the next one is 22.08. And here it is 42.08. And here it is 63.08. Like this, you have to find out the peak top to know the peak position. That is 285.08. And here another peak is 495.08. And here it is that is, here it is 517.08. And here another peak is there, that is 524.08. And here it is 530.08, like that, right? So here another one peak is there, and here another one peak is there, right? So like that, we have to list all our peaks like this, right? So here, for example, I have selected 1, 2, totally 8 peaks I have selected, right? So for these 8 peaks, we are going to attribute with, peak element information. To find out the element information, we have to go to this particular website called NIST XPS database. Simply just go to Google and Google as NIST XPS. and you'll get one website, that is srdata.nist.gov, right? So if you open that particular link, you'll get this particular, you'll be landed up in this particular link. So here, go to this identify unknown spectral lines. So it's having some error. I'm reloading the page. Yeah. Identify unknown spectral lines. Yeah. So here you have to select the binding energy. And here in the binding energy, you have to give that particular peak position, right? So first peak's position is 21.08, right? 21.08 like this, right? So here the correction we can give it as 1, or if you know very precise about your chemical shift correction and all, you can give 0.2 or 0.1 like that, right? So I'm giving 0.2. So for binding energy means for elemental survey, you have to give the correction as 0.5 or 0.2 only. At the maximum you can give 0.5, right? If it is another calculation, that is the Auger parameter calculation is there. Indexing is there. For that you have to use some greater error here, right? So I'll tell you later that. Here it is 21.08, that is 0.2, right? So here it came for, so something I know about my material, so it might be for oxygen 2sp, right? So that is 21.08, very near to that. I have oxygen 2s, right? So here I can write in the Excel sheet, I can write this is for oxygen 1s. Like this you can write. Then next one is 43.08, right? 43.08. Now press search. So now here it might be for 43.08, right? So very near to 43.08. We have arsenic or calcium, right? So my element might be either calcium or arsenic. So here I can write calcium 3s, arsenic 3d. Calcium 3s or arsenic 3d, right? So like that. Yes, 3D, right? So like that we can, from here you can search for a particular peak and you can name that particular peak, right? So for example, if it is 495.08, 495.08. That is simply tin itself, right? So that is SN 3D 3/2. So SN 3D 3/2. Sorry, it should be here. It is C1s, right? All of us know already that is C1s, and then 517.08. 517.08. Pressing search. This website will be somewhat slow. Okay, you have to wait for some time. And this particular peak is for 517.08 is for vanadium. That is 517.08. Very near to that, it is V2P 3/2. V2P 3/2. Like this, you have to name each and every peak, right? Then 530 is oxygen 1s. So I'm quickly typing that. And 632.08. 632.08. I'm going to type it here. 632.08. I type. I'm using the same binding energy itself. If I press it, I'll get this there is in data means there is in data means this is not, what is that, matching with the binding energy, available binding energy in the database, right? So we have to search it for some other options. So you just go to Auger parameter, right? And one important thing is whenever we are going for Auger parameter, this particular tolerance should not be 0.2. It should be increased to 10 because Auger energy peak will be having some, range of, energy which will be coming out. So it won't be a exact precise line or something like a delta function. It will be coming as a, profile itself. So here we are not giving the exact 0.2 difference. Here we have given 10 difference, right? So now if I press search, just see here, it is for calcium, right? So this is the Auger parameter for calcium. So the 20, that is for 43.08. We have already, right? So 43.08, we have already the calcium as an element in our compound. So for that particular calcium, now we have this Auger parameter also, right? So this is the calcium's Auger parameter, that is LMM calcium. So here we have to write Ca calcium LMM Auger line, right? So we know the meaning of LMM. So you can refer any theory or you can simply Google it, you will get it. And the same way, 974.08's index is vanadium LMV. So this is the Auger peak once again for vanadium, right? So now we have surveyed all the elements present in my compound. So my compound is having a very small intensity of calcium. Then oxygen 1s is there. Sorry, this is for oxygen 2s. Sorry, oxygen 2s, and here it is oxygen 1s, and tin 3D 3/2 is there. Tin is there, and vanadium is there. Calcium is there once again. That is vanadium is there once again, right? So my compound is having the major elements of V, and then O, and then SN, and small amount of calcium. Like that we can write. So right now, I know my compound is tin doped vanadium oxide. So it is there. All the three elements are there. Calcium's peak's intensity is just see here, calcium peak intensity is very, 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 very less. The first one, this one is very, very, very less. This might be coming from the water what I have used for this particular chemical synthesis, right? Sometimes my students might not have cleaned the vessels, at ultimate cleanliness. So this calcium might be coming from my water source also. So my compounds, all other peaks are available for me. That is vanadium, oxygen, then tin. All the three peaks are there, right? So this is for carbon 1s, adventitious carbon 1s. And here it is for 495 is for tin. That is a tin doped. And here one peak is there. That is 516. That is for vanadium. And here the 530 is for oxygen, right? So tin doped vanadium oxide is my compound. And that particular compounds, each and every element is, confirmed by this particular survey scan analysis, right? So with this survey scan analysis over. So simple, only thing what we have to do is, here you have to copy it to a new sheet, and here you have to correct the chemical shift here by using the carbon 1s peak position, and then corrected data should be plotted, and from the corrected data you have to find out the peak position, each peak position, and you have to make a table like this, and using this particular NIST XPS database, you have to index each and every peak, right? So for each and every peak, you have to give the elements and its core shell, value should be assigned, right?